Hi, I'm Sophie Kowalik, and this is my glider project. So the requirements and purpose was to use research conducted from past lectures and the internet to construct a glider out of balsa wood that could go at least 20 feet without breaking when it is hand thrown. This will be tested on flight day if I am successful. The initial prototype design that we must create, test, and alter is measured by success with my completion of the project checkpoints. I named my glider the Painted Lady because of the glider's butterfly-shaped wings and tail. Before I research type of tails, I research horizontal and vertical stabilizers. Horizontal is used for longitudinal stability and it prevents drag, while vertical supports lateral stability, which is the side-to-side motion. The three types of tails I was considering was T-tail, V-tail, and the conventional tail. The T-tail's pros are its efficiency and pitch handling because it keeps the tailplane out of the turbulence generated by the wings and the fuselage. However, it does have a low speed and can cause deep stall, rendering the elevator ineffective. The V-tail reduces the weight and drag, especially for aircrafts with high centers of gravity, because it is combining both horizontal and vertical components into one. This increases stability if done correctly because it is very difficult to manufacture. The conventional tail is the most common tail because it's easy to create and has good pitch and yaw, but causes drag due to weight. The different wing designs I considered was elliptical, tapered, swept-back, rectangular, and delta. The elliptical's pros is that it's the most efficient with the lowest possible drag. However, it is difficult to manufacture, especially evenly and balanced. The tapered wing has improved lift and reduced drag for long periods, improving stability and maneuverability. This wing is used in high-performance gliders where efficiency and balance are crucial. However, it can cause high-induced drag and low aspect ratios if the wingspan isn't large enough, due to the way you have to sand and shape your wing. The swept-back wing is usually used on fighter aircraft because of its speed, but it does have less lift. The rectangular or straight wing is commonly used because of how easy it is to manufacture and create a dihedral, but it isn't the best option for efficiency or for a glider because of its weight. The delta, similar to the swept-back wing, is used because of its speed on heavy pieces of aircraft, but it does cause lots of drag and weight. The adhesive options I considered were hot glue, Gorilla Glue, CA glue, and masking tape. Hot glue's pros are that it's fast drying and easy to remove, which is good for keeping things together temporarily, but it's not great for a piece of aircraft that has high strength requirements. Gorilla Glue has a strong seal that's good at filling in space. However, it does take a long time to dry, which can be hard to put the dihedral on, and it's not reliable for thin materials such as the balsa wood I'm using. CA has incredible strength and flexibility because of its durable and versatile bond. It's rarely used on wood, however, but the way it heats up creates a very strong bond that is quick drying for the dihedral I would be using. Masking tape is useful because it's easy to remove and reapply. However, it can't take a lot of impact that a glider needs. When making these decisions, I focused on what could be used on high-performance gliders, what was light, and what improved stability. Tapered wings create good stability and balance because of the way it decreases the drag. I specifically chose the middle taper because it holds the best balance and can create the best lift. The V-tail is lightest in weight due to the reduction of control surfaces and is capable of having great stability if manufactured correctly. For the adhesives, I will use CA for my final design because of its strength and efficient drying time. But to hold on to the added mass, I'll be using masking tape because it will make it easier to test how much weight to add. Hot glue will be used on my prototypes because it's fast drying and can easily be removed if I need to change things around. Initial design. The wing location is 2.8 inches away from the front of the fuselage. I did this to maximize the static margin and hope to move the center of gravity along with it to help with longitudinal stability. The wing size is 10 by 2 with a root chord of 3 inches because of the aspect ratio to keep it within 4.5 and 7.5. I added a 5-degree dihedral because too high of an angle causes drag and instability. The fuselage is 10 inches because I wanted to make sure I had plenty of material to work with. I was planning on increasing this to test stability. Each V-tail fin is 2 by 3 at 45 degrees. I did this based on how horizontal components of a tail should be about 20 to 25% of the wing area, and the vertical component should be about 40 to 50%. The Painted Lady prototype runs center of gravity was 2.8 inches from the front of the fuselage. The C of 4 was 2.5, so it was pretty good. The static margin was 2.2 because the neutral point was about 5. The mass I added to the nose was 15.2 grams, and the glider without the mass was 14.9, making the total mass 30.1 grams. The aspect ratio was 5, and here you can see that the paperboard was used for the tail and for the wings, and then cardboard for the fuselage and clay for the mass. Here is the Painted Lady Prototype 1 test flight. It ended up going 20 feet. It did have a slight tilt to the side, which might have been because I didn't taper them evenly in balance because it's hard to sand them correctly. Here, I tested different angles of attack. I ended up finding that the stall angle was 40 degrees and the best angle to use was 30 degrees. For alterations with sizing, I want to increase the fuselage and wingspan to create a higher aspect ratio that gives a lower drag and a better glide angle. These larger wings provide a greater surface area for generating lift, allowing the glider to stay airborne for a longer duration. The fuselage was increased to create a larger static margin for stability. I decided to also test how rounded corners will decrease potential drag. I wanted to test also how the glider's performance will be affected when the whole thing is made by the same material, cardboard, compared to my first prototype, which had different types of cardboard in it. Prototype 2 design. So on the right here, it shows that I increased the wingspan and the fuselage span to 14 inches, and the V-tail is now 4.25 by 2. The new center of gravity is 5 inches from the front of the fuselage. Because of these new lengths, it caused an increase in the static margin by an inch to 3. For the neutral point was about 8 inches, increasing the longitudinal stability. The aspect ratio went up to 7, and the weight drastically increased to 56.2 grams because of the cardboard material. I changed to quarters because it's easier to keep track of the weight and it won't dry up when adding weight to the nose cone. Test flight 2. It ended up going 30 feet. The increase in stability shown from the aspect ratio and static margin increased the distance by 10 feet. I tested with and without rounded corners, and it only made a distance of 1 foot. The angle of attack used was 20 degrees, and I assumed that when I make it with balsa wood, it would go farther because balsa is lighter and reduces drag, so I consider this test a success. Final prototype. All these measurements are the same for my prototype 2 because these measurements increased longitudinal stability and it increased the distance successfully. Although the dimensions were the same, the density of the material changed, so I had to add enough weight to the nose until I got a center of gravity of 5 inches to get the static margin of 3 again. I did keep the dihedral 5 degrees because I didn't want to risk adding too much and causing drag. The mass added was 17.8 grams and the total weight ended up being 38.9 grams. This is my final glider flight. Here we can see that this blue part you see right there, that's the 30-foot mark. I made that there because I wanted to show that the last prototype went 30 feet and I wanted to see how the balsa wood compared. It landed right there, which is about 28 feet. The angle of attack I used was 25 degrees. The stall occurred that I tested for was 50 degrees. The glider was stable and it had a straight course due to the tapered middle wings balance. However, it still lacked lift to pick itself up and increase that distance. My calculations for the lift coefficient was 72.02 and the drag coefficient was 290.15. I ended up having to calculate the average velocity with 3 different test flights, and I found the aspect ratio. Conclusion, yes, it met the requirements. It was 16 by 16. It flew a minimum distance of 20 feet. It ended up going 23 feet. It stayed put together during the flight and only had a hand-thrown propulsion. So what I liked about my glider was it had a unique detail and middle tapered wing, and it had impressive stability, even though it was hard to manufacture. What I would improve is it was very fragile, so I would try to 3D print a guide for the wings and the fuselage. I would also try a T-tail design because it increases lift by sticking the elevator out of the way of the air being pushed from the wings. And there's my citations.